In the last lecture, we began our paleontological exercises, starting looking at fossils from the Big Bang, leftover particles from the earliest moments of the universe's history, both using them to check that our theories of the earliest moments of the universe's history are on the right track, but also to put constraints on the stuff that makes up the universe and to learn about our universe today. Big Bang nucleosynthesis gave us a very nice way of measuring the total amount of ordinary matter in the universe, the total amount of atoms, of stuff made of mostly of protons and neutrons and electrons. The answer is there's not enough stuff there to be all of the matter we perceive in the universe. There must be dark matter that is something else. Today we're going to look at an even more basic relic of the Big Bang, which is photons, in particular the cosmic microwave background. The background radiation left over from when the universe was about 400,000 years after the Big Bang. You might have already heard of the cosmic microwave background in the context of providing evidence for the Big Bang theory. When the CMB was first discovered in 1965, as we will talk about, it was still plausible to believe that the Big Bang wasn't right. There was an alternative theory called the steady-state cosmology, in which the universe had been expanding forever, and more matter was continually being created in empty space. There was not some hot, dense, original state out of which everything came. But the Big Bang model made a very specific prediction. There should be a leftover cold radiation from that initial hot state. That's what that leftover radiation is. Today, it is the cosmic microwave background. Also, the cosmic microwave background is important because it provides static for your television set. If you have a non-cable TV, about 10% of the static that you see on your screen is actually from photons coming out from the cosmos in the form of the cosmic microwave background. We only figured that out after we discovered it by other methods. But for today, what we're going to be interested in is not really the existence of the microwave background, not really using it to test the Big Bang theory, but to look at the tiny variations in the temperature of the microwave background from place to place. The very early universe is smooth, and the earlier you go, the smoother it is. So when we talked about Big Bang nucleosynthesis, we treated the universe as exactly the same everywhere. The microwave background is the first time when the slight ripples in the universe, the slight perturbations in density, make an appearance, and they affect things being a little bit different from place to place. So the CMB provides us with a snapshot of what the perturbations in the universe looked like 400,000 years after the Big Bang, and by both looking at what they looked like then and comparing to what they look like today, we can learn a tremendous amount about the constituents of the universe. Ultimately, the CMB will provide us independent evidence, both for dark matter and for dark energy. Dark matter we will talk about today, dark energy we will get to in a later lecture. So, the game we play by now should be familiar. Start with the universe now and wind the movie backwards. Ask what happens when you take a volume of universe today and squeeze it like a piston, make everything more dense and squeezed into a smaller place, increasing along the way the temperature. As the scale factor goes down, the temperature goes up in exactly an inverse proportion. So if the microwave background that we observe today is at about 3 degrees Kelvin, a very cold set of radiation particles, when the universe was 1/1000th its current size, it was at about 3000 degrees Kelvin. The reason why that's an important temperature is that's the temperature at which the photons were sufficiently hot that when they were banging into atoms, they had enough energy to strip the electrons away from the atoms. In other words, at moments before, when the universe was 1/1000th of its current size, there was too much hot radiation to allow atoms to exist. You had free electrons running around unattached to atoms, and you had free protons and other atomic nuclei. They wanted to get together, but they kept running into hot photons, which prevented them from doing so. So all of this was happening at, like I said, about 400,000 years after the Big Bang. More specifically, 380,000 years after the Big Bang is a slightly more precise moment when it happened. We know that from the Friedmann equation, from the equation in general relativity that relates the expansion rate of the universe to the stuff inside. So what the Friedmann equation is telling us is that at earlier times than that, the universe was hot enough that everything was ionized. Individual atoms were just a nucleus and the electrons were moving freely. What that means is the universe was opaque. Remember that photons like to interact with charged particles. They can interact with atoms. The photons cannot go through this table. It is opaque. But if atoms arrange themselves in the right way, photons will just go right through them. The air in this room has the property that photons of visible wavelengths travel right through it unimpeded. However, when you're ionized, when you have free electrons going around, no photons can go through you unimpeded. Those photons will keep running into those free electrons, and that will make them bounce and turn in a different direction. If you were alive during that era of the universe's history, which you couldn't be, it was too hot, it's like living on the surface of the sun, but if you put your hand up in front of your face, you couldn't see it, because a photon could not make it from your hand to your eyeball without bumping into a whole bunch of things. It was as if the universe was immersed in a thick, soupy fog. They couldn't see anything. And there were a lot of photons. There's a rule of physics that says when something is hot, it gives off a lot of radiation. This is called black body radiation because it doesn't matter what color the thing is or how it's excited the different atoms or anything like that. It's just that any lump of stuff at some fixed temperature will be giving off radiation all by itself. This is how you can see people in the dark with infrared goggles. Their body temperature is enough that they're giving off thermal radiation, black body radiation. It's the same reason why a heating element will be glowing red. It's just giving off black body radiation. So the early universe, we know, had to be filled with radiation because it was at a high temperature. It has a black body spectrum, and you can actually test that by observing the microwave background today. So the moment of the universe becoming about 3,000 degrees Kelvin is when recombination happens. Recombination is the moment when electrons can finally get together with protons and with other atomic nuclei to form atoms. Recombination is a word from atomic physics that is used for when you take an electron off of an atom, the electron goes back. So you've removed it and now it is recombining. Sometimes people say you shouldn't use this in cosmology because it's not recombining. That was the first time these things ever combined. That's being a little bit too tricky, in fact, because in the real world what happens, even in cosmology, is that a typical electron and proton will combine and recombine many, many times at that temperature of about 3,000 degrees Kelvin before they finally settle down. But when they do settle down, when you formed atoms out of the ions that you used to have, the universe has now become transparent. You had a lot of radiation running around, you had black body radiation suffusing the universe, and now that radiation stretches freely throughout empty space. It can go through the gas of hydrogen, and of course it can go through the dark matter and neutrinos. They don't bother you. So that photon now has a path that instead of being really, really short, can stretch for billions of light years. So all that radiation was being created at every point in the universe. So us living here right now can look around and see that radiation coming at us. Nothing ever happened to it from the moment of recombination, 400,000 years after the Big Bang, until today when we bump into it. So the universe becomes transparent. When it becomes transparent, the temperature is about 3,000 degrees Kelvin. That's actually pretty hot. That's the kind of temperature you see, for example, at the surface of the sun. The sun is not emitting microwaves, it's emitting visible light. That's why we see it. But of course, what happens is the universe expands by a factor of 1,000 in between recombination and today. So the light that was given off at recombination was actually similar to what we see from the sun, but it gets redshifted. It gets stretched in wavelength by the expansion of the universe. Today it has reached the microwave regime. The wavelength of this stuff from the early universe is the same wavelength as what you use in your microwave oven to heat things up. It really is that kind of microwave. So this whole story of the early universe emitting black body radiation, it being opaque when the universe was ionized, and then suddenly becoming transparent when recombination happened, was worked out in the late 1940s and the early 1950s by George Gamow and his students, Ralph Alpher and Robert Herman. We heard about Alpher and Gamow in the previous lecture. They also worked out Big Bang nucleosynthesis for the first time, and the prediction that there should be something called the cosmic microwave background was actually made by these physicists as a spin-off of their work on primordial nucleosynthesis. So they're making these predictions. It was about 1950. They didn't have very good astronomical data, but they were still able to predict that the microwave background should exist, and it should have a temperature of something like 5 to 10 degrees Kelvin, was their guess. It turns out that it's more like 3 degrees Kelvin, but that's extremely good considering the quality of data they had at the time. Again, however, they were ahead of their time. They made a prediction. It was about 1950. No one had the technology to go look for this stuff. It was very unclear to Gamow, Alpher, and Herman when they were writing their papers whether anyone would ever be able to detect this microwave background radiation that they were predicting. As it turns out, in 1965, Arno Penzias and Robert Wilson, working at Bell Labs, succeeded in detecting the cosmic microwave background. This was back in the day when Bell Labs, owned by Bell Telephone, would do basic research just because it was interesting. They were not trying to build anything better. Of course, they were also trying to build better things, but they were invested in just doing research because they wanted to learn about the universe. So radio astronomy was a hot new topic at the time, and Bell Labs was heavily invested in radio astronomy. Penzias and Wilson were young radio astronomers who had built new receivers and were trying to calibrate them into looking at different objects on the sky. They built a large horn-shaped antenna located in New Jersey, in Holmdel, and they were trying to bring it online for the first time. Penzias and Wilson didn't know that there was any such thing predicted as the cosmic microwave background. They were interested in looking at radio astronomy sources, stars and nebulae that were inside our galaxy. But when they were trying to calibrate their new telescope to make sure it was working, they kept getting noise. They kept getting some background buzzing that they couldn't get rid of. The reason why they were puzzled is because no matter which direction the telescope was pointing in, they got the same kind of noise. To them, this meant that it was a problem with the telescope, not something they were seeing in the sky. If it doesn't matter where you look, it's probably because your instrument is faulty somehow. But they went through every single check they could think of, trying to remove this noise from their instrument. They even climbed into the horn to scrape off the pigeon droppings from the inside of the instrument, because they were a dielectric material giving off microwaves. Eventually they realized, we cannot get rid of this signal. We are actually receiving microwaves from the sky. Purely by accident, they were informed by a friend of theirs that there was a pre-existing prediction for the cosmic microwave background, number one. And number two, there was another group down the street at Princeton, New Jersey, who knew about this prediction and were trying to detect it. Bob Dickey, who was a physicist at Princeton, and his graduate students, Jim Peebles and David Wilkinson, knew about the cosmic microwave background. Dickey had predicted it independently after Gamow, and they were engaged in an attempt to build a receiver to detect it. They were building something on the roof of the physics building at Princeton University, not knowing that there was a much better telescope that was by accident down the street discovering the same thing. So in 1965, Penzias and Wilson published a paper. Peebles, Roll, Dickinson, and Dickey and Wilkinson published a theoretical paper explaining what Penzias and Wilson had seen, and these two papers appeared right next to each other in the Astrophysical Journal. Penzias and Wilson's paper was entitled A Measurement of Excess Antenna Temperature. They didn't say out loud that what they had detected was in fact the relic radiation from the Big Bang. They admitted in the paper this was a very promising interpretation of it, but just like Hubble years before, they were good observers. They were telling you what they saw in the universe. They were leaving it to you to interpret where it came from. So Penzias and Wilson won the Nobel Prize for their work in 1978. Nobody won any Nobel Prize for predicting the cosmic microwave background. Alpher and Herman, who were still alive at the time, Gamow had passed away, thought that they were going to win the Nobel Prize because they had predicted this wonderful thing that was then observed. But they had predicted it so early that everyone forgot. And even though they kept trying to tell people, they never really got the recognition that most people think now they deserve for doing both Big Bang nucleosynthesis and the cosmic microwave background. You do, by the way, feel bad for the poor photon from the cosmic microwave background. We're talking about a photon which, in the very early universe, kept scattering off of electrons. Then the universe became transparent, and that photon traveled across tens of billions of light years without bumping into anything, only to land in New Jersey to be detected by some physicists. But it was for a good cause, because the microwave background today is very useful to us to doing astrophysics. So the important thing when we were discovering the cosmic microwave background was that it was there, measuring the temperature of it. The cosmic microwave background at that time, to the best observation anyone could make, was perfectly smooth. You look in every direction of the sky, you get the same temperature. But everyone knew that couldn't be strictly true. In our current universe, it's not perfectly smooth. It's more or less smooth on sufficiently large regions. So if you go back in time, it must have been pretty smooth, but not perfectly so. That meant that there must be fluctuations in the temperature of the cosmic microwave background that grew into the larger perturbations we see today. You could even figure out how big the fluctuations in temperature should be. They should be 1 part in 100,000. So if you see the microwave background being at a certain temperature in one point, if you go over to a point next to it, it should be different by 10 to the minus 5, by 1 part in 10,000, by 1 part in 100,000, sorry. So that is where the action is today in measuring the perturbations in the temperature of the cosmic microwave background and using them to characterize the behavior of structure formation in the universe and the ingredients that go into that structure as it forms. It was finally detected, the tiny variations in temperature in the microwave background, in 1992 by the COBE satellite that was put up by NASA. COBE stands for Cosmic Background Explorer, and the COBE satellite was the second most complicated satellite NASA had ever put into orbit after the Hubble Space Telescope, which was the most complicated one. So COBE just sat there taking data. There was at the time when COBE was launched, there was a previously existing experimental result which brought into question the fact that the microwave background was really a black body. There was some people who had put up a telescope who had on a rocket, and they had measured a deviation from the black body spectrum. People were worried about that. The very first thing that COBE did was to verify that the spectrum of the cosmic microwave background was indeed a black body. This was a talk at a meeting of the American Astronomical Society that got a standing ovation, which rarely happens at talks at the American Astronomical Society. The fact that the COBE Explorer was able to verify that the microwave background was really a black body was big news. A year later, it went beyond that, and it found the tiny fluctuations in temperature from place to place in the cosmic microwave background. And a few years later, in 2006, John Mather, who was the boss of the telescope as a whole, and George Smoot, who was the boss of the specific instrument that found the temperature fluctuations, were awarded the Nobel Prize for doing that. Since 1992, since COBE found that there really are fluctuations in the temperature of the microwave background, we have gotten much better at measuring these fluctuations. We've developed a large retinue of different ways to take pictures of the cosmic microwave background. Here is an image of one such cosmic microwave background experiment. This is the Boomerang experiment, which was launched on a balloon in Antarctica. The idea of a balloon is that you get up above most of the atmosphere, so you have a clear region of the view of the sky. The idea of Antarctica is that there are winds that go around the continent. So this is a very unusual kind of physics experiment. You build it, and then you launch it in a balloon. So you build your experiment, and there's a balloon, and it goes up, and the wind carries it off to the east, and you see it go that way. And then you wait 2 weeks, and you see your experiment coming back to you from the west, because it has gone, circumnavigated the continent once. In the course of about 2 weeks, you can collect that much data, and then you push a button, and it falls down, and you collect your data in the experiment. That was the Boomerang experiment. There were other similar experiments. There are other telescopes observing the microwave background in Chile, in California, and at the South Pole, where we've gotten very good at measuring the microwave background in different ways. Perhaps the best image we have of the microwave background comes from the Microwave Anisotropy Probe, or MAP. It was renamed the Wilkinson Microwave Anisotropy Probe, or WMAP, after Dave Wilkinson, who was one of those graduate students of Bob Dickey's in the early days, who became a pioneer and sort of the grandfather figure of cosmic microwave background research. He was an important person on the WMAP satellite, and he passed away just before the first results were announced. So here's an image of WMAP itself. It is a satellite, so it can observe the whole sky. That's the real difference between a satellite imager of the microwave background versus a balloon or a ground-based image. If you're sitting on the ground, or even in a balloon that is not very high above the ground, you can't see what's going on beneath you in the earth. If you're a satellite, you can get a 360-degree view of everything that is happening on the cosmic microwave background. And what WMAP did was exactly that, and it returned this image, an iconic picture in cosmology, a map of the tiny temperature fluctuations in the cosmic microwave background. The blue regions are a little bit cooler than average. The yellow and the red regions are a little bit hotter than average. This is the snapshot of what the universe looked like about 400,000 years after the Big Bang. So what do we learn from this? Where did this picture come from, and what is it telling us? The point is that we don't have any way of predicting precisely where a cold spot will be and a hot spot will be on the microwave background, any more than we have any way of predicting where a galaxy will be in the sky. What we have are statistical theories that predict we should get so many perturbations like this, so many perturbations like that. So what you need to do is to observe all of the microwave background and characterize the statistics of the different patches of hot spots and cold spots. That is something you can compare to a set of predictions. So how do you make that set of predictions? You are going to consider the life of a blob of stuff. So we imagine that we have a little blob of stuff at very, very early times in the universe's history, a little blob that has a tiny bit more density than the surrounding plasma. So it wants to contract. Under the force of gravity, this blob of stuff wants to get smaller and more dense. But it may or may not succeed in doing that. What happens to this blob of stuff will depend on how big it is. If the blob of stuff, for example, let's say at recombination, let's say it's 1 million light years across, the particular blob we're looking at. Well, the age of the universe at recombination is only 400,000 years. So a blob of stuff that is 1 million light years across doesn't have time to collapse. So when we look at the cosmic microwave background, it turns out that every angular size that we're looking at that is greater than 1 degree corresponds to a physical size that is greater than 400,000 light years. So on scales greater than 1 degree across, when we look at the microwave background, we're looking at things that did not have time to evolve. They are not telling us anything about the evolution of stuff in the universe because they didn't have time to evolve themselves. So let's look at stuff that was smaller than that. Let's look at blobs of stuff that did have time to evolve. What happens to them? So you have an overdense region. You have a region of the early universe with slightly more matter in it. So when it begins to evolve, it will contract. When stuff contracts, just like the universe or a piston or anything else, it heats up. So what initially happens is the region of stuff, which is slightly overdense, contracts, heats up, and that forms a hot spot that you could observe on the microwave background. But you need to ask what will happen next. And what happens is exactly like a sound wave here in this room or anywhere else. You have a region of increased pressure, but what happens is that pressure pushes things away and things bounce back and become less dense than they were before. So you have a blob of stuff that contracts under its own gravity, it heats up, becomes hot, but there's also more pressure. That pressure pushes against it, and that same blob expands and becomes underdense and cold. Once it becomes underdense, it is surrounded by regions that are denser than it is, and the same process happens. The blob bounces back and forth. It is truly an acoustic wave moving through the primordial plasma, just like a sound wave moves through this room. A moving region of high pressure, low pressure, back and forth. So that would be interesting all by itself, but there's more physics going on. There's two important pieces of new physics besides just this oscillating sound wave. One is that it doesn't oscillate forever. It is damped. Just like when I say something into this room, you hear a slight echo, but you don't hear an echo forever because the sound waves bump into stuff and die away. These oscillations in the early universe will eventually damp out and stop because things are mixing. Things are moving from dense regions to underdense regions. So if you look at very small regions, very small blobs of stuff, it is true that they oscillate, but they damp out and stop. So for very small parts of the microwave background, you don't see that much anisotropy. You don't see that much variation from direction to direction, very much perturbation in the temperature of the microwave background. On small scales, things have had time to smooth out. On large scales, things have not had time to evolve. It's the medium scales that are interesting. That's when things can collapse, heat up, and then expand and cool down. But the other new piece of physics is, of course, dark matter. The story that I was just telling of stuff collapsing and heating up is a story of ordinary matter. It's a story of atoms, of protons and electrons. When I say heat up, what we mean is stuff bumps into other stuff. It exchanges energy, and that's what causes it to heat up. But dark matter is collisionless. Dark matter just collapses. Dark matter doesn't heat up. So in the first stages of this process, you have an overdense region. It's a nice, very convenient feature of the universe that if a region is overdense in ordinary matter, it is also overdense in dark matter. They go hand in hand. So when things begin to collapse, both the dark matter and the ordinary matter collapse together in the same place. But the ordinary matter heats up, becomes high pressure, and then uncollapses, becomes less dense, but the dark matter just keeps collapsing. So the dark matter just keeps collapsing, the ordinary matter is oscillating back and forth. And what you get is a series where the ordinary matter, is in phase with the dark matter, then out of phase with the dark matter, then in phase and back again. Back and forth, the dark matter is either helping the ordinary matter collapse or hindering it from expanding. In other words, when we look at the cosmic microwave background, when we look at the pattern of splotches of hot and cold spots on the sky, certain sized splotches are being helped by the dark matter, certain sized splotches are being hindered by the dark matter. You will get more variations in temperature at certain scales than you will at other scales, if there is such a thing as dark matter. So this was a theoretical prediction that was made very cleanly and crisply ahead of time. People knew what to look for. Then when WMAP and other satellites and other experiments were looking at pictures of the microwave background, they were able to then do statistics on what kind of patches existed, how big the different splotches were, how much variation you had in temperature from place to place. The answer is that you need about 5 times as much dark matter as there is ordinary matter in order to explain the pattern of temperature variations in the cosmic microwave background. That number, 5 times as much dark matter as ordinary matter, should be familiar to you. That is the number that comes out of taking the total amount of dark matter that we infer from dynamics and compare it to the total amount of ordinary matter we infer from Big Bang nucleosynthesis. In other words, completely independently from either galaxies and clusters or Big Bang nucleosynthesis, the cosmic microwave background is telling us that we need non-baryonic dark matter. The patterns of hot and cold spots in the microwave background would by themselves be enough to imply that we need dark matter in the universe. It is very, very good for the standard cosmological model that this implication from the CMB matches implications we had from other ways. Of course, it would be even better if it didn't match. If it didn't match, that means that we're learning something new, that we don't understand what is going on, that it's a clue to something else that we haven't yet figured out. But it's nice to have a theory that works. What the microwave background is telling us is that the theory of dark matter plus ordinary matter works. That a universe in which 5% of the critical density is in ordinary matter, 25% is in dark matter, is one that fits not only galaxies, clusters, not only Big Bang nucleosynthesis, but also the cosmic microwave background. So that is a lot of information that we were able to extract from these patterns of hot spots and cold spots on the microwave background. But we're not done yet. The CMB turns out to be a treasure trove of information, and we're going to get a lot out of it. It is certainly evidence for dark matter. We'll show in a later lecture it is also evidence for dark energy. The microwave background implies very, very strongly that the total density of the universe is equal to the critical density. So far, we've been using the critical density, the density of stuff that you would need to make the universe spatially flat, as just a convenient way to measure how much stuff there could be in the universe. It might be that the actual density is only 30%. The microwave background is telling us that that's not right, that the actual density of stuff in the universe is 1 in units of the critical density. The actual density we have is critical. The universe is spatially flat. So in other words, not only is there dark matter more than ordinary matter, there's also something else. There's also something that is besides the ordinary matter we see, and that is going to be dark energy. That's one thing that we get from the microwave background. Another one is testing our theories of the early universe. In a later lecture, we will talk about inflation. Inflation is our best candidate theory for where the initial fluctuations in density came from. Inflation is very much a speculation at this point in our history. We don't know whether it's right or wrong, but it makes some predictions. It makes predictions for how things appear in the microwave background that have turned out to be true, but we're still trying to do better. We want to know not only the temperature of the microwave background in that direction of the sky and that direction of the sky, but inflation makes interesting predictions for the polarization that we see in the cosmic microwave background. So we are by no means finished with observing the microwave background. We're building new satellites. The European Space Agency is building a satellite called Planck that will be launched in a couple of years to measure the microwave background to unprecedented precision. We're hoping that as we study this relic radiation from the Big Bang with greater and greater instruments, with higher and higher accuracy, we will continue to learn more and more surprising things about the universe.